Welcome back, everybody. This is the video about section 6.3, square root functions. This is exactly where we left off right before the break, but I figured we should take a little bit of time to put down on the blackboard here the things we need to know about the parent square root function and transformations to that parent square root function, especially regarding the domain, range, and end behavior. So if we recall the parent function itself, for all square root functions, the parent function is f of x equals the square root of x. This is our familiar curve that has one endpoint at the origin and then heads off to the right and upward forever. One important feature of this particular curve is that it has to pass through the point 1, 1. Because, of course, if f of x is the square root of x, then f of 1 equals the square root of 1, which is just 1 again. So not only does that endpoint occur at the origin, but it also passes through the point 1, 1. But more to the point for today's discussion, I think we're interested in the domain, the range, and the end behavior of this particular parent function. Now remember, the domain has to do with the allowed x values, or the x values that have corresponding y values on the yellow curve here. Our goal here is to read the graph from left to right in increasing x values and see where we start to see y values associated with it, or where we start to see a curve at all. Well, we don't start to see a curve at all until the point where x equals 0. And then from there on out, we have a curve. So we can say that the beginning of the domain is the x point 0, but then it goes on forever to infinity. If we're interested in the range, we need to do the same thing, but we need to do it in the y direction. In this case, we're interested in reading from the bottom of the graph to the top of the graph and finding which y values are allowed on the graph. Well, there's nothing allowed below the y value of 0 here, but anything above 0 is totally allowed, and we see it on the yellow curve. So our range here also begins at 0 and runs to infinity. The end behavior of this graph is really just determined by what's happening at this arrow here, as this arrow heads off. As x heads off to infinity, the y value of the graph, better known as f of x, also gets bigger and bigger, and heads off to infinity. That's as x is moving in this direction. As we have x move toward the negative direction, well, there's a certain point at which it stops. So we're not particularly interested in where y goes as x heads off to negative infinity, because negative infinity isn't even in the domain of the function. Instead, all we care about is where x heads to 0. And we want to know exactly what happens to the function at that point. Well, as x heads to 0, we know that we're heading back into the origin, so f of x also has to head to 0. This is the basic behavior of the parent function, f of x equals the square root of x. But we're also interested in the entire family of functions that are square root functions, and we have a general form for that. The general form of the square root function has 3 important numbers in it: our a number, our h number, and our k number. The a in this particular case has 2 important functions. A determines the vertical stretch, or how tall this curve gets relative to the parent function. But it also determines vertical reflections, which is important in the case that a is less than 0, or a is a negative number. When a is a negative number, it flips the square root function vertically. The h value is our horizontal shift, or horizontal translation. As we've discussed several times, in this function we always see x minus h. So when h is positive, we will always see x minus h. But when h is negative, we will see h minus some negative number h, which will appear as x plus a number under the radical sign. What does this have to do with transformations? Well, in this case, we have a transformation to the right. In this case, we have a transformation to the left. The final value we care about here is the k value, which is probably the easiest to deal with of all. This is our vertical shift number, or a vertical translation number. For positive k, we have an upward shift. For negative k, we have a downward shift. In graphing square root functions, one of the most important things to remember is what's happening to the endpoint. We know that the endpoint has coordinates h, k. So whatever the horizontal shift and the vertical shift happen to be, that will be the number of units that that endpoint moves away from the origin. Another important thing to remember about transformations to the parent function has to do with the vertical stretch. Remember that when a is greater than 1, we're going to have a stretch, and when a is less than -1, we have a shrink. Now, just to point this out on the graph that we drew just a second ago, we know that this curve runs through the point 1, 1. That is the parent function. If we transform this by changing a, it's going to either stretch that point 1, 1 higher or lower. So for 1 unit over, we might move more than 1 unit up, we might move less than 1 unit up, and it depends on the value of a. The key to all of this is as follows. So for that first unit from the endpoint that the graph moves to the right, it's also going to move up a units. In the case of the parent function, that a was 1, so it moves over 1 and up 1. If a is larger than 1 and we have a stretch, we're going to move up more than 1 unit for that 1 unit that we move over. If a is less than 1, we're going to have a shrink, which is going to compress the curve and mean that for that first unit that we move to the right, we're going to move less than 1 unit up. Let's say this is our parent function, and we're interested in graphing a new function, g of x equals 1/4 the square root of x. Well, all this means is that we've changed the a value from 1 to 1/4, which means for this first unit that we've moved to the right, we're not moving a full unit up anymore, we're moving 1/4 of that distance. So when we draw this curve, it's now going to run through the point 1, 1/4. Let's take a look at Desmos to see a few examples of how this actually operates. Looking at the parent function in Desmos of f of x equals the square root of x, we see just as we did before that the origin is on the graph, and so is that point 1, 1. The domain starts at 0 and heads to infinity. The range also starts at 0 and heads off to infinity. But let's look at what happens when we start to transform this a little bit. Now, the green graph we're showing is the square root of x minus 5, which is all under the radical sign, and then a minus 1. We can identify the three numbers here as a equals 1, h equals positive 5, and k equals -1. So what we've seen here is no vertical stretch at all, but we have in fact translated this curve so that the endpoint is no longer at the origin. It's moved down by 1 unit. That's our k value. But it's also moved to the right by 5 units, which is our h value. So all we've done here is a translation on the original curve. Let's combine that with a vertical stretch. Now the blue curve, f of x equals 4 times the square root of x minus 2, has no k value, but it does have an h value, which means that we have a horizontal shift. And that horizontal shift in this case, well, h is positive 2, which is why we have x minus 2, which means we've shifted over positive 2 units, or 2 units to the right. That's our h value. Now clearly this blue curve grows a heck of a lot faster than the red curve. In fact, it should grow 4 times as fast. So, whereas with the original red curve, we had growth of 1 unit to the right and 1 unit up from the endpoint, we should see something slightly different from the blue curve. In fact, we should see 1 unit to the right corresponding to 4 vertical units. But since we started this curve with an endpoint of an x value of 2, when we move over to the right by 1, we're actually moving to a point 3 units away from the origin. So the x value of the point that's 1 unit away from the endpoint is now 3. But where we had a y value of 0, we now have a y value of 4, because this is growing 4 times faster than the parent function. Let's clear all of this out and see if we can identify the equation of a curve given what it looks like on the screen. Here's a new curve for us to figure out. Well, we know that we have at least some translation here, and the reason we know that is because the endpoint of this curve is no longer at the origin. It's now all the way up at the point 0, 2. Well, we know that hk will always be the coordinates of the endpoint. In this case, hk equals 0, 2. So we can start writing this equation in general form by saying it must have whatever the value of a is, x minus 0, and plus 2 has got to be our k value. So we've already figured out 2 of the 3 important values here. The only thing we need to worry about now is the a value. We can figure that out by understanding how far this curve moves up when it moves 1 unit to the right of its endpoint. Well, let's see. This is the y value 3. So this is the y value 2.5. And if we move over 1 unit to the right of the endpoint, we're moving up exactly 1/2 unit here. So the point that's sitting on this curve, 1 unit away from its endpoint, is 2.5. Well, let's see, how far have we moved upward? We started at the y value 2, so we've only moved up an additional 1/2 unit. That tells us exactly what our a value is. So we can complete our function, f of x, by inputting the a value. We can also just get rid of that h value. Since it's 0, there's no need to put it in the equation. Plus 2. Let's figure out one more of these. Here's a new function, also a square root function. This one, of course, looks distinctly different. The first thing that we should notice is that this has been flipped vertically, and that can give us a clue right away as to what must be the case with the a value. We know that the a value has got to be less than 0 in this case. We can start there even before we know anything about how big a is or what kind of translation has taken place here. But let's go back and look at the translation again. Well, from the parent function, we've moved 2 units to the left, but we've also moved 1 unit upward. So that gives us our h and k values right away. If we want to write this out as f of x, we have some negative a value, and then in the square root sign, we have x plus 2, because we had a negative h movement, and we've got to have a positive 1 out here as our k value. Well, great, we're almost there. All we need to do is figure out that value of a. So for 1 unit of movement away from the endpoint, we need to figure how far we've moved in the y direction. So here is our endpoint at the point -2, 1. If we move 1 unit in this direction, we're actually moving 1 unit down. So a plus 1 in the x direction corresponds with a negative 1 in the y direction. We know with the parent function f of x equals the square root of x that that movement of 1 unit to the right usually corresponds with 1 unit up. In this case, we've come 1 unit down, which just reminds us that we have a negative a value, but that a value is still 1, because for the movement of 1 unit to the right, we've also moved 1 unit down. And that gives us our entire function here. I'll put the 1 in for emphasis. So now we see the vertical reflection, the translation left 2 units, and the translation upward 1 unit. I think that's all we need to talk about with square root functions today, and we'll see where we stand with all of that next week. Thanks for your time today.